Let's record. Let's record. All right, remember contrapositive? Remember that from yesterday? That's the one that's correct. Yeah. So for any if-then statement, if that statement is true, the contrapositive will always also be true. There's only one time where all four of them are true: the statement, inverse, converse, and contrapositive, and that's in an if and only if statement, right? Which is generally a definition or a postulate. So, symbol, logical, mathematics, logic, the symbols can be kind of weird, but that is the symbol for not, right? So if a function is not continuous, it's not differentiable. And we know that because continuity is a necessary precondition. So we really have a whole mess of examples now where a function is not differentiable. All of these are examples where it's continuous and not differentiable, right? Sharp turn, also known as a cusp. A vertical tangent, which can be sneaky because it is smoothly connected. And then a genesis point of a graph, you could say, a starting point of a graph. Whether or not it's a vertical tangent or not, it could be a starting point that launches out the slope of 1. Because to be differentiable, it has to be two-sided. There's no one-sided definition like there is for continuity. And now we have the whole can of worms, any discontinuity, right? Jump, holes, VAs, and what was the other discontinuity that we learned about that you're not responsible for? But I know you still have it in your head. The oscillating discontinuity. Remember that? Yeah.
Oh, yeah.
Cool. Yeah. All right. So let's look at example 13. It says for f of x equals that, determine if f is differentiable at x equals 1 by using the alternate form and then by doing a continuity argument. So if you look at this, it's a piecewise function. And it's made up of a line with the slope of 2 to the left of -1 and at -1. And it's made up with another line of 2 to the right of -1. Now, a casual observer who really doesn't know much about calculus might look at this and say, oh, the slope is 2 everywhere to the left and the slope is 2 everywhere to the right. So because the slopes are the same to the left and right, it must be differentiable at -1, yeah? But we saw last time that that is not necessarily the case. See if I can still find it, right? I drew that little slanted line that is broken. And if it's not continuous, it's not going to be differentiable. All right, so I'm going to use the alternate form. And remember, you're not going to have to set up and use the alternate form on the AP exam. But it's a wonderful thing because, remember, it not only checks the slopes from both sides, it checks the y values. It checks the connectivity. It's a machine that does both. So let's go ahead and set it up. The limit as x approaches -1 from the left of the difference quotient, right? F of x minus f of -1 all over x minus -1. That makes it easy to remember the alternate form. Do your math homework. It's just the difference quotient as x goes to the x value. And I'll go ahead and set it up on the right-hand side. The limit as x goes to -1 from the right, f of x minus f of -1 all over x minus -1. Now remember, the thing that is the same in both of these is the function value. And for that, we're going to be using the top piece each time, because that's where the equal sign is, right? We're going to be using the top piece for that. But the f of x, the f of x part is what varies depending if we're coming in from the left or right. So from the left, we're going to be using the top piece. And from the right, we're going to be using the bottom piece. Okay? So let's go ahead and make it specific now. Keep writing the limit as x goes to -1 from the left. F of x from the left is 2x minus 1. Minus, what is f of -1? Well, I haven't done that yet. Plug in a -1 there and you get -3. All over, at this point, I can call it x plus 1. Okay? I'm going to simplify before I plug in. So that's going to give me a 2x, and that's going to be a -1 minus a -3. That's a lot of negatives. How about -1 plus 3, which is plus 2? all over x plus 1. And now if you plug in your negative 1, you get 0 over 0. Okay. Well, this is a real easy factor and divide out problem. I'll factor out the 2 in the top, and I get x plus 1 over x plus 1. And at this point, the x plus 1s do what? Divide out. Now, I'm trying to teach the pre-calc kids, and most of them are catching on. But remember, when you divide out the x plus 1s, what should you do in the denominator? You should, well, you could put a 1. Some of you are already doing it because you're not even realize that's the answer I'm fishing for, but put it in parentheses, right? It doesn't, you don't need them there when it's standing alone, but when you divide them out, it shows that you're taking the whole quantity, all right? Yeah, now you could put a 1 down there. That's a good thing to do as well. And then this line here that I'm going to write, the limit as x goes to negative 1 from the left of 2, this is an optional step, okay? But could you stop there? Let's say you did write that. Is that the answer? If the limit's still in front, have you really evaluated the limit yet? So now the limit of a constant is just that number. So that's why that step is not necessary. If you realize that everything divides out, then as soon as you plug in, or if there's nothing to plug in, you write your answer, you don't need the limit anymore. But if you do, for cleanup purposes, make sure you go one step further. Now, is that surprising to say that as this graph comes in from the left, it's approaching a slope of 2? Because it's 2 the whole time, right? I'm a 2, I'm a 2, I'm a 2, 2, 2, I'm a 2, I'm a 2, I'm a 2, 2, 2. Let's do the other one. Is this going to be 2 as well? I mean, look, it's also 2x plus 1. No, we can't assume that, right? Because it takes into account the continuity part, it may not come out to be 2. If it did come out to be a 2, then we would say it's differentiable at negative 1. The function f is, because 2 equals 2. All right, let's go ahead and set this dude up. The limit as x goes to negative 1, from the right, is 2x plus 1. And now minus, to figure out what goes next, do I plug a negative 1 into the bottom piece, question mark? No, it's still the top piece. That's where the equal sign is, and it's still a negative 3. Okay, all over x plus 1. Really, really heavy on the notation here, right? It's almost like a burden. I have to write the limit each time, but you know what? At least it's easy. So we get 2x, 1 plus 3 is plus 4, all over x plus 1. Never not first, right? Direct substitution, never not first. So I plug in a negative 1, and I get 0 over 0, of course. Yeah. No, this is the same as this, which is negative 3. Yeah, right. That's the mistake that some people use. They want to plug this negative 1 in there, and then they'll get a different number. So that's what locks in the connectivity part when you're checking the slopes. F of negative 1 can only be one value. It's the top one. So yes, right? And now when you plug in here, you don't get 0 over 0. You get 4 minus 2 in the top, which is 2 over 0. 2 over 0 is not an indeterminate form. What does 2 over 0 mean? It's some type of infinity, right? Non-zero over 0 is some type of infinity. I don't know if it's positive infinity or negative infinity, but it doesn't exist. That limit doesn't exist. So in that case, does 2 equal d and e? No, right? So in this case, you could just say 2 does not equal d and e. I don't know if that's the best argument, but you know, it doesn't work, right? Both of them have to exist, and they both have to equal each other. How about d and e equals d and e, right? Oops, I don't know, right? Or I mean, I'm trying to avoid all this, right? Let's label this. Let's label the top part. I'm going to call this big R. How about this now? Since R does not exist. I'll write it out in words. Otherwise, you're going to have to say, since the right-sided limit does not exist, or since, and then you have to write this whole expression again. Yes, absolutely. As long as there's not a sharing violation, like if you're using R for something else in the problem. But yeah, you can label it, and then you can refer to it. Since R does not exist, comma, F is not differentiable at x equals -1. Well, you can. I mean, it's not an untrue statement. Yeah, I mean, I would accept that because it's true. Yeah, it's not the best argument, but it's not untrue, so it'd be fine. All right, so you're not ever going to have to do it on the AP exam, but you know, before the shortcut rules were around, that's what we had to do. Now, moving forward, especially once we get to 2.2, which is the power rule, we're going to test for differentiability in a two-step process. We're going to say, okay, if it has to be continuous to be differentiable, let's check for continuity first, okay? Because it's easier to check. So let's go ahead and do that over here. Continuity, let's get our machinery up and running. We want the limit as x approaches -1 from the left, but now not of the difference quotient. We want it of f, and then we want f of -1, and then we want the limit as x goes to -1 from the right of f. Road, bridge, road, remember? All right, now the limit from the left of the function is the top piece by direct substitution. That's going to be -3, which is the same as the function value. It's the same company building the road coming in as the bridge. And now the limit from the right, I can plug into the bottom one, which gives me -2 plus 1, which is -1. Okay, so now I could say this, since -3 does not equal -1. Which -3 am I referring to? Both, or either. Yeah, take your pick. Since -3 does not equal -1, comma, can I go straight to saying f is not differentiable? Very good. F is not continuous at x equals -1, comma, and now I could say, and therefore, or and so, that's a shorter word, and so f is not differentiable. Diffable. No, they don't grade you on grammar. Yeah. But there you go. You can't just make the leap from -3 doesn't equal 1, therefore it's not differentiable. You got to string the arguments together. -3 doesn't equal 1, therefore it's not continuous. And now if it's not continuous, it's not differentiable. So that's how we'll do it in the future. That's a lot faster, a lot shorter. Now, in the future, if we did do this and we got all three of them being the same number, now the function is continuous, which means it's possibly still differentiable. Then we will find, as I mentioned yesterday, then we will be able to quickly find, using a different technique, a piecewise derivative function very quickly. And then we would do the same thing we did on example 7. Then we would look just at the slopes to see if they're the same. And if the y values are the same from both sides and defined, and the slopes are the same from both sides and defined, then we can say the function's differentiable there, right? And then we can guarantee it's smoothly connected, not with a vertical tangent line though, okay? All right, awesome. So the alternate form, it's almost like you got to savor it because you're not going to really use it much ever again, unless you do so, you know, on your own. All right, questions on that? Alternate form. All you're going to be expected to do is deconstruct it. Yeah? Deconstruct it. Which, yeah, I'm trying to find that example. It was up here, right? Example 9. You will be told it's a derivative, by the way. Again, I mentioned that because without that, it's not really obvious. But when you deconstruct the modified form, You still will be told it's a derivative, but there's a telltale sign there as h goes to 0. All right, this is a pretty long section, right? I mean, 9 pages, a lot of good information. Nothing is wasted. All right, there's one last version of the derivative that I just want to point out to you, expose you to it, because it's important. But I'm not going to test you over it, and nor over the AP exam. Okay, it's called the symmetric form. The symmetric form, and much like the modified form and the alternate form, it's the disposable version. It gives you a numeric value. So there's only one that gives you the variable function that you can then use repeatedly on the back end, and that's the formal limit definition. So here's what the symmetric form does. Let me show you kind of the graph. It'll make more sense. Let's say we have this function f of x, and I am interested in finding the slope of the tangent line right here at C. Okay. I'm going to choose that other point over here that we've been choosing. Okay. Now for this one, I'm going to call it C plus H. So I'm going to be going back to calling the distance between the point I'm interested in and the point that I have to use H. But instead of just choosing those 2 points and leaving C fixed, the point I want, and letting H go to 0, I'm going to choose yet another point over here. That is the same distance away from my point of interest C on the other side. Call it C minus H. All right. Now, when I find the slope of my secant line, I'm going to use those 2 points, which, let me see if I can get this to line up close enough. If it doesn't work, just make your points bigger. See that? There you go. Now, the slope that I'm after, remember, is the red one. And it may be that if I just find the slope of the secant line using 2 points equally spaced on either side, that might be a decent approximation of the one I want. It almost seems as if they're parallel-ish, right? And, you know, that's going to vary from curve to curve. But the idea is the same, okay? I have these 2 points, C plus H, f of C plus H, and then C minus H, f of C minus H. If I find the slope of the secant line, here's what it's going to look like. M sub secant is the change in the y values, f of C plus H minus f of C minus H, all over the change in the corresponding x values, C plus H minus parentheses C minus H. Okay, that's the slope of the secant line. If we simplify that, the numerator just kind of doesn't really do much. But the denominator, what happens? Your C's will cancel, and you're left with H minus negative H, which is really H plus H, or 2H. So not surprising, you know, the width is 2H. Now, here's the magical step. Turn it into calculus. The slope of the secant line becomes the slope of the tangent line, which becomes f prime of C, if all we do is we put the limit in front of this dandy of an expression. And of course, we let H go to what? 0, yeah. So instead of leaving one point fixed and letting the other point essentially slide towards the one we want, these 2 points here that are equally spaced, they will both be essentially approaching the one we want. We have 2 points converging, but it's going to approach the same thing in the end. When H is, you know, intolerably small or infinitesimally small, they're all going to be approaching the same thing. So it's just another way to look at it. Now, why is it important for y'all? Well, because this is how your TI-84 calculators are programmed. TI-84 calculators are programmed, believe it or not, they're number crunching machines. So they can find numeric slopes. They can't find derivative equations in terms of x, but they can find numeric slopes. And if you ask it to find a numeric slope, it does the symmetric version. So let's go ahead and look at example 14. Using your calculator, if f of x is equal to 3 minus 6 absolute value of x plus 1, find the following. Well, before we do that, let's go ahead and see if we can sketch this dude from our knowledge of parent functions and transformations. You want to try? Oh, I want to try. F of x equals, I'm going to go ahead and write it, 3 minus 6 absolute value of x plus 1. We want to put it into standard transformation form, okay? Which, if you remember what that looks like, the 3 in the front really goes at the back, x plus 1, and that's really about all we have to do. So just looking at the transformations, the parent function, let's go ahead and sketch that off to the side. That's y equals absolute value of x, and of course, that's your V for victory graph, right? That's the graph that comes in, and it's at a 45 angle here, boom, and it leaves at a 45-degree angle there. So we know by default it has a slope of -1 coming in on the left and +1 on the right. And what would the derivative value be anywhere to the left of 0? Like, what's f prime of -4? When I say f prime of -4, that's just another way of me asking what's the slope of this graph at -4, and what would the answer be? -1. Yeah, instead of calling it y equals, let's call it g of x, just so I can refer to it. So what's g prime of -4? It would just be the slope of this graph at -4. It's -1, right? What's g prime of -400? -1. What's g prime of -0.0001? -1, right? What would g prime of 1,000,000 be? +1, right? Same thing, anything to the right of 0. What about g prime of 0, though? Not just nothing, it doesn't exist. Yeah, doesn't exist. Because that's where we visually have a sharp turn. The slope from the left is -1, the slope from the right is +1. -1 doesn't equal +1. So just bear in mind, if I ask you for the derivative, it's asking for the slope. Now, let's go ahead and do what this graph looks like, because this is a transformation. We'll draw a new x and y axis. The negative in front does what to any function, including this one? Flips it across the x-axis, right? And then the 6 is a vertical stretch by a factor of 6. Guess what that's going to do to your slopes? It's gonna sextuple them, right? Your slope is now going to be 6 and -6, respectively, depending on whether it's increasing or decreasing. That's your new plus or minus slope. And then the +1, +3, those are your shifts. That picks the whole graph up and moves it left 1, up 3. So that's the new coordinate of your vertex, -1, 3. So let's go there. -1, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Now, just to make it as accurate as possible, since I'm going to be crossing the y-axis, what is f of 0? What's the y-intercept? 0 plus 1 is 1. The absolute value of 1 is 1 times 6 is 6. 3 minus 6 is -3. Oh my gosh. How was it? Yeah, boom. So there's another one. So the graph is going to look like this. I'll use red. It's going to come down like this, straight line, snap. There we go. And then it's going to look like this on the other side. So there's f of x right there. That's the graph of f of x. So notice now I could ask you these questions. Let's just answer them without a calculator first. What would f prime of -2 be? This is -1. Yeah, so -2 is over here. It's the slope. The slope anywhere to the right of -1 is going to be 6. So you can answer it left to right with an equal sign, or you can answer it straight below without an equal sign. But yeah, it goes from increasing now with the slope of 6 anywhere to the left of -1 to decreasing. What would be the slope at 0? F prime is 0. Yeah, -6, okay? So again, when I ask you for the derivative, I'm asking you for the slope. And if it's made up of a line, that's easy to find, right? Rise over run. All right, everybody, what would now be F prime and -1? It would be DNE, right? It would be DNE because that's where the sharp turn is. All right, sweet. Now, we didn't use the symmetric difference quotient for that. We just used our knowledge of the graph. But let's quickly see what the graph on the calculator tells us. Are we going to run out of time? Please, please. 2 minutes. Okay, that should be work out. If Symmetric works, come on, tech. Come on. Browse, yeah, browse. Okay, there. Load it. All right, there we go. I'm going to type it in. Here we go. Type it in. Scoot over. There we go. Type it in. Oh, I'm getting nervous now. The clock's still ticking. I can't stop it. Oh, I messed up. 3 minus 6. Math number 1 again. There's the absolute value. X plus 1. All right, now watch this. From the home screen, not from the graph screen, you can find the derivative. It's math 8. I wrote that on here. Math 8. See that? Math 8. It's going to give it to you in Leibniz form. You don't know what it is yet, but it's the derivative with respect to x of my function, alpha trace number 1. That's in y1. And we're going to evaluate it at -2. That'll have meaning to you later on. But this is the derivative of the function that's in y1 at -2. It gives you 6. Nice. Now hit second enter to recall it. Scroll back down here and change the -2 to a 0. That's evaluating the derivative at 0. -6. Orale. Now let's look at second enter. Let's do -1. -1. 0. Holy moly. Does the fancy new color calculator say 0 as well? Uh-oh. Let's all take our calculators back to the Walmart and tell them that they're not working and see if they can give us a refund. Why did the calculator tell you it's 0? It's obviously wrong. Because of the symmetric difference quotient. Watch. It's picking a value to the left and to the right. And if you do that all the way up until you get closer and closer, because of the symmetry, what's the slope of that line? It's a horizontal line the whole way. And so the calculator says, if it's 0, then it's got to be 0 at the vertex. And it's R-O-N-G wrong. You are the boss of your calculator, not the other way around. Your calculator uses the symmetric difference quotient. All right, have a great lunch. We're done with this section. Perfect timing.